Okay. Okay, so let's start. Today we have Aylin Garcia Soto from astronomy department. It's just in the Dartmouth College. She's in PhD student with working with the Professor Elizabeth Newton. And our research focuses on magnetic field related to M-dwarf photometric and spectroscopy variability in the form of spots, flares, and spectral lines to understand the surface features and also the magnetic field dynamo of those stars of these M-dwarfs. Yeah, and of course, the combination to exoplanet transit studies, that's her research area. And also she's a member of NASA Pandora SmallSat mission. And as well as previous is a member of QI, Deputy Manager of NASA MIT TESS mission. So Aylin, take it away.
Thank you. Also, I can't get rid of this meeting's being recorded. So sorry.
Oh, it is. I mean,
we don't see it.
We don't see it.
Okay, I see it then. It's fine. Okay, cool. Thank you for introducing me. Yeah, I'm a grad student at Dartmouth College, and I work with Elizabeth Newton, and as I'm told, an alum from your university, Ben Rackham. Yeah, so for starters, I will do a little outline of the talk. First, we're going to discuss the background. It's very important to know your planets. So to know your planet, you need to know your star. So it's very important to know your star. Then we're going to talk slightly about magnetic fields. I apologize. I think it's important, but it's not going to be a big portion of the talk. Then we'll discuss a little bit more about magnetic proxies and comparing them to each other, a little bit about observations and samples, and then we'll get into more of the results. So we have short-term variability in M-dwarfs, and we also have selection effects, and then the summary. So for starters, we're going to talk about M-dwarfs in comparison to other stars and M-dwarfs in relation to exoplanets. And so we have three different spectral types here. We have M, K, and G. In terms of sizes, an M-dwarf is 60 to 10% smaller than the sun. So in comparison, somewhat looks like this. They're more abundant than the other. They live longer. And if you were to look at transits, so this is when a exoplanet passes in front of a star, then you get a much bigger effect on your light curve. So this is a light curve is flux over time. And so the same planet will give you a much deeper transit. And so if we were going to do a best host tally, it's 1 to 0. The other good thing about M-dwarfs is that because they're so small, their habitable zone is much closer in. So it's much easier to find exoplanets there. So that gives it another nice plus. However, M-dwarfs are very, very active. They're more active than our sun was when it was young. It had, if you were to look at X-ray radiance, it gives 400 times more than the sun does today. So that's not quite. But actually, or well, actually, as I have on a slide, there's more issues with M-dwarfs, as people in exoplanets do know. You cannot assume homogeneity on a surface of a star, and because of that, you get a lot of extra negatives. So it affects radial velocity measurements, it affects transit measurements, and it affects exoplanet transmission spectra. Emphasis on the last one. The first two are about basically removing stellar activity from your exoplanet detection methods. But the last one's very important, especially now that we have JWST up. So what is that? So if you have a transiting planet, when it passes in front of a star, the atmosphere of the planet, you can get the transmission of the atmosphere of the planet because the star is getting its photons is getting observed in the atmosphere of the exoplanet. And so you can get an idea of what the exoplanet atmosphere looks like. However, there's an issue with that because the you really need to know what that surface looks like in the first place. It's not homogeneous, as I mentioned before. It has a lot of different surfaces. So I drew this emoji. This is my M-Dwarf emoji. You wear glasses because I wear glasses. But essentially, I put spots on it and I put flare ears on it. And if you pick a spot um, on it, you see that it's darker than the surrounding surface of the star. And so that spot can actually have a transmission, it can have a spectra that looks different than if you just take the entire spectrum of the star. So if the planet is passing in front of a spot, that would look very different than if it wasn't, even if you get the spectra beforehand of the star. And so you have to be very careful. Some M dwarfs even have water in their spectra, which is something we really care about in transmission spectroscopy. So where do these spots come from? And that's sort of why we have to talk a little bit about magnetic fields, because we only know it in context of the sun. So in the sun, there is an 11-year cycle where you get minimum surface features or maximum surface features. It isn't always 11 years, but it basically is 11 years. And the thing that causes this, we think, is called an alpha omega dynamo. This this figure is very complicated, but let's just think of the magnetic field lines as a rubber band. So here we have a star. We have poloidal magnetic field lines. That's your rubber bands. And you have its rotation axis or its spin axis. The way that we're going to talk about this magnetic field is think of stretching and twisting a rubber band, essentially. For this dynamo to work, we are limited to we think of the inside of the star as having three different regions. We have the convective zone that works because hot bundles go up as it gets hotter and cool bundles go down as it's cold, like water boiling, basically. That's the convective zone. The radiative zone is basically, think of fire being like heating the bottom of your pan. And the region between these two zones inside the star, there's a name for that splitting region, and it's called a tachocline. In this region, because there's differential forces on both sides, it's thought to be sheared as the star rotates. And so these rubber bands are being stretched around the sun. And because there's turbulence in the convective zone, because of how it works, the rubber band gets twisted, essentially. And from these twisted loops, magnetic loops, you can get features on your surface. So this is where the spots come in. I drew only the north half of this image because the south half looks the same, but it would be too messy if I did both. So in the top part, you see the movement of a spot as it evolves. Basically, it originates underneath, it rises to the surface around the equator, it moves towards the pole, and it goes back down. That's sort of how it evolves. It goes upwards, at least on the sun. So what is the dynamo for M dwarfs? Well, the thought is that because some M dwarfs actually look like a miniature sized sun, it might be that for that. However, some M dwarfs don't have a radiative zone. They're fully convective. And so they're also still very magnetically active. So what is the explanation for that? And so that might mean that the tachocline is not that important. But because I'm not a theorist, the ways I look at the magnetic field is by studying proxies. So this is another picture of the sun where you have different magnetic proxies. For the corona, you can look at X-rays. For photosphere, you can look at flares or spots. For the chromosphere, which is the layer above the photosphere, you can look at Lyman alpha. You can look at H alpha and calcium H and K. And these all can tell you a little bit about what the magnetic field is doing. So let's talk a little bit about what a flare is, because that's important. So back to the rubber bands. A flare is, if you have a magnetic field loop and that loop crosses in the middle, that top part will actually come off and fly away at relativistic speeds, and then the bottom part actually reconnects. So that's what magnetic reconnection is. And that also gives you a flare. Another proxy is spots. So if you have a spot on your surface and you're staring at your star for a long time, as the spot moves out of your field of view, essentially, the brightness of the star increases because these spots are dark. And when it moves back into the field, it decreases in brightness. And so if you look at a light curve for a long time, you get an amplitude, but you can also get the rotation period of the star because it has surface features. Another proxy that I'm interested in is H alpha. So in a normal regular star that's not really magnetically active, you'll get H alpha in absorption. And I'm sure that's what has been taught in star classes because it's true. Like that's the natural state. However, if you heat up the chromosphere a lot, you can actually get H alpha in emission. So for at least the first half of the talk, the majority of these stars have H alpha emission. I'm not looking at absorption. And this is sort of an example of what that would look like as a spectra. You have counts on the y-axis and you have wavelength. So I've highlighted H alpha. You cannot miss it. It's very big. This is an M dwarf spectra. And for this spectra, I also was able to look at H beta, gamma, and delta, which are other lines in the chromosphere at different levels. And they're also in emission. And why I'm looking at these is because I only have access to this range of the spectra, but also they're very interesting and they can tell you a lot about variability. Okay, so let's start comparing these proxies. One of the two that gets compared a lot is rotation period and a magnetic activity index. In this case, H alpha, but they've done X-rays, they've done flares, they've done calcium H and K. But for my purposes, I'm going to talk to you about H alpha. So here you have a plot where you have y-axis of H alpha strength. It's also luminosity, but I just wanted to make it simpler. And then you have the rotation period on the x-axis. Anything on the left is faster and anything on the right is slower. And by that, I mean that it's like 1 day rotation for the left side and like, I don't know, 80 days rotation for the right side. And the color bar here is amplitude. So it's the same amplitude I mentioned before. And you can see that there's a somewhat plateau and then there's a very huge decline. And so if you look at that plateau, kind of, you can sort of see that the amplitude is actually, there's more there's more bigger amplitudes in that region than there is when you rotate slower. And so if you change the way this plot looks and you have amplitude on the y-axis now and mass is the color bar, you can kind of see it has a positive correlation, but it's very, very scattered.
Could you actually give the idea about how large the strength and the amount of amplitude and strength and then mass? Because there is no
Yeah,
range.
sorry. The mass goes from 0 to 0.6 or 0.4, I think, because our highest was 0.45. And the amplitude range is not that big. I think I have numbers later on.
Okay. Okay.
Yeah.
What about the period? What are the
Oh,
ranges
so
of the
the
period?
period for this paper, I think they went from, I believe Elizabeth had gave it a region, so it's from 0 to 10. Those are considered
Okay.
fast. And then anything above 10 is considered slow.
All right. Thank you.
Yeah, so for this image, you see where that very large error bar is? That's sort of the break. Anything to the left of that is like 10 days, and then anything to the right of that is greater than 10 days. That's a good point. Sorry about that. So yeah, if you rearrange, you see somewhat a scattered relationship. And for around mass of 0.20, which is not labeled here, but think of it as like once you're getting dark, like the middle of the color bar, you can somewhat see that there's a larger H alpha strength. So the darker points are bigger than, let's say, 20. 0.20 solar masses. And so the idea for this was maybe the scatter is related to when each observation was taken, because the amplitude stuff is photometry and the H alpha stuff is spectra. they're not taking at the same time unless you specifically so for this paper it wasn't taken on time. It was just whatever was in the literature for I believe actually it just wasn't taken on time. Sorry. Um, and so what my part was to recreate this, but actually take both observations at the same time to see if maybe there was just we were at different magnetic field phases or something. So I used TESS. Um, the limit that comes from TESS, that's a transit survey, is that everything has to be less than 10 days. Only currently, we're looking at longer periods, but because one sector is 27 days and you need at least two humps to get a period, the limit is half of it. So it's like 10 days. So everything that we're going to talk about in this first half is less than 10 days. And spectroscopy, because when we know when Tess is observing, I can go to the mountain and observe. And this is a picture of me in Halloween. I've met an alien. Really fun time. I'm just kidding. But like the limit for this one is that it has to be brighter than 16 magnitudes. And so we recreated the plot. And no, it's pretty much still scattered. We also did it for H, beta, gamma, and delta. And they're also very scattered as well. And I know what you're thinking. You're looking at this and you're like, those are horrible, large, like horribly large error bars. Why did you even show us this? They're not error bars, actually. So now we're going to transition a little bit to short-term scaled variability that we found without meaning to, but it has been seen in the literature before, where this quote-unquote error bar is not an error bar, is the range of H alpha strengths. And so this means that within one observation, the H alpha strength varied by that much for each star. Sorry, varied by the length of that for each star. And so to get a clear view of what is this showing is we're going to do like curves for H alpha. So that means we're going to plot the strength versus time. And we're also going to do it for TESS, since for some of these we have them exactly simultaneous. So for starters, here's a TESS like curve. We have brightness over time. The time bar will be presented shortly. We have the black, the gray shows 20-second cadence. The red dots are bent cadence. So every observation was taken every 2 minutes for the spectra. And the gray is every 20 seconds for TESS. So we just bend it so we can sort of see what it would look like if we had taken it every 2 minutes for TESS. And you see that the flare here becomes a bump. So it's not very descriptive. And that's sort of one of the things people use for TESS proposals as a evidence that you need shorter cadence for flares. And so to identify the flare, I can do it manually, but that's not scientifically accurate. And so what we use is we use this package called Stella from Adina Feinstein. This package has been trained on 2-minute cadence data from TESS, and it knows, and it's been trained on not flares and flares, and so it does a pretty good job. Here's another light curve, but this time I've added the probability from Stella of that it's a flare. And so you see that the yellow, it does a very good job finding them. The yellow parts are what the flare is. And so, and you also see rotation variability in there. And so that's what we used. I don't know if you can see it, but there is now a shaded region where that flare is. The next thing is breaking down the width part. I called it width. I should have changed it, but because there's another thing called width. But essentially, we're taking the area under the curve and we're finding a rectangle that has a similar like line width. Essentially, the two have the same area, and that's called equivalent width. And in this image, you're just seeing H beta change over time. And so we're doing equivalent width for every single change or observation. And so now we have our light curve. On the top, you have the TESS, and on the bottom, you have the spectra. And strength here just means equivalent width, but it's a similar thing as luminosity. They mean how much strength there is. And so now you see that the time axis is filled. So this was observed for about 2 hours. And you can see around where that flare is, there might be a little bump there. But then if you look further along the line, you see there's still some variability that's not really corresponding with TESS, right? There's like other bumps and there's no TESS bumps to correspond with it. The same thing was done for a different star. So this is now a different star. You see that Stella has highlighted some peaks in there. I would like to say that 20 seconds is not enough for a flare sometimes, is because these are just a few dots. You can see it because it stands out of the plot, but like if I had done scatter, you can tell it's like a single dot that's being represented. And so if we have the same plot for this one, you see actually now that the flares are very, very clear in the spectra rather than TESS. So it's the reverse. I would like to note that that third one, around 16 minutes, is actually much larger. It's just in order to make it easier to see the second bump, I removed some of it. But they do happen around where Stella said it would, except for maybe that last part. And that last one is a very long flare. Well, in my opinion, there's longer than that. There's ones that last hours. So essentially, we're seeing two different kinds of flares. We're seeing white light flares. So that's the ones we saw in TESS, and we're seeing non-white light flares, and that's the ones that we don't see in TESS, but they do exist. We see these both in the sun. Um, so the difference between the two seems to be that there's a weaker magnetic field. So right now I'm showing you how just by looking at H alpha and having photometry with it, you're actually already getting some information about the magnetic fields. So those were two different stars and they had different kinds of flares. So now I'm changing gears completely. I'm still going to be talking about amplitudes, but no longer talking about specific flares or spots. So I do need to define something first. So we're going to talk about stellar obliquities. So what is that? That is the spin axis angle. So if you have this geometry of a star, the stellar obliquity is the angle between the orbits. Oh, I actually wrote that wrong. My bad. It's the orbital spin axis angle. So it's the orbit of the planet and how the star is spinning. The angle between those two is the obliquity. Stellar inclination is the spin axis of the star and the line of sight, so where we're seeing it. And then orbital inclination is the orbital axis and the line of sight of us where we're seeing it. If you have an obliquity of 0, this might be an easier way to see it. That means your star spinning and your planet's rotating in the same direction. If you have one of 90, I like to call it rotisserie chicken because there's an offset of 90. So think of it as Uranus has spinning on its side, basically. And if you have a stellar obliquity of 180, your spin axis and your orbital rotation are in different directions. And so in terms of population, if you look at the cooler stars, so stars that are less than 6,000 degrees, you actually see that they're pretty well aligned. So this means they are less than a 30 degree obliquity. And this break is actually called the Kraft break. And that's when the magnetic, the convective zone becomes deeper. And so that tends to be true for solar-like stars. And for those, they seem to be well aligned. But if you look at the other half of the Kraft break, the hotter stars, the ones that are hotter than the sun, they actually have a larger range of stellar obliquities. And so I have all three, 0 to 180, basically. Anything around that range. The other thing I wanted to mention is its relation to amplitude. So because stellar inclination and stellar obliquity are related, stellar inclination are also related to amplitudes. So here's an image I have above where it shows what the star looks like, what its spots look like on the star at 90 degrees stellar inclination, and then what it looks like if the inclination was actually 30. And if you look at the light curve below, you actually see that the amplitude for the one that's at 30 is much smaller than the one that's at 90. And so if you know your inclination and you know the amplitude, you can kind of say something about the obliquities. That's what Mazeh et al. 2015 did with Kepler amplitude. So what they did is that they found the amplitude for stars that are presumed single, so they don't have transiting planets. I changed this to mean control stars because we don't actually know if they have planets or not, especially if they're not transiting. I also call them transit hosts. And they did it for KOI. So these are planets found in Kepler. And they noticed that below the craft break, so I have this red arrow, you actually have the amplitudes of the KOIs being greater than the amplitude for the control stars. And above that, you see the reverse. And the idea is because the amplitude of the KOIs is greater, that means you're seeing well-aligned stars, systems, which is what the population studies before has said, and that didn't use this method. So they're like from 0 to, we can't say the number of degrees for obliquity, but that's the idea that they seem to be well aligned. And above the craft break, it's the opposite. You see the single stars having larger amplitudes than your KOIs. Something I forgot to mention about the KOIs is that we assume its stellar inclination is 90 because you're seeing the transit. It's not always the case, but it is usually close to 90 stellar inclinations. The referee for this paper, as they said in the paper, mentioned that what about active stars? So stars are they have a lot of activity going on. There are planets missing around them. We could be missing planets missing around them. So how do you adjust for that? What this paper did is that they created two samples from real life data. They created sample P and sample R. Sample P is essentially known transit hosts or known stars with transits. And there's 115 of them. And then sample R is the control stars with known periods that may have a planet that we don't know about. And those are around 4,000 stars. From the two samples, they defined a signal to noise detection represented by that equation, where it looks at number of observed transits, transit duration, stellar inclination, planet radius, and the Kepler 3-hour photometric noise. And the detectability was basically to see if they can recreate this 115 sample. And the signal to noise has two values, basically ones that are easily detected and ones that are barely detected. And they ran the simulation 100,000 times, and then they plotted this histogram of amplitudes. So we're seeing the amplitudes. And we see two things of this is that they plotted a white dashed line to represent the median from the simulations. And the median from the simulations were actually much higher than the median from that plot before. And then you also see the cyan dash. And that one shows that the median for the KOIs were actually much lower than the median from that first plot I showed you. The first one is thought to believe because of the selection effect. The second one is thought to believe a geometric effect. So this may show that planets preferentially like to be in a rotisserie position, so a 90 position. However, the one thing about this paper is that it's not just 6,000 K stars that are really active. M dwarfs are very active. That paper didn't go as low as they could because Kepler didn't really look at M dwarfs. So Ben Rackham's idea was to redo this study, but for TESS, for the cooler end. Before we did that, though, we revisited Mazeh et al. 2015 with a newer Kepler samples, and I split the two samples into things that rotate less than 13 days and things that rotate faster than 13 days. And I recreated that plot where you have amplitude on the y-axis and effective temperature on the x-axis. Mostly what you see is that we don't have many we don't have many planets around the slow rotators, whereas we have way more planets on the slow rotators. So we're missing stars around these active. Sorry, we're missing planets around these active stars, and so that Mazet et al. Result was mostly looking at these inactive stars. So there is another selection effect in the cooler end. Now I've recreated that plot for TESS. And I know you're thinking, you're looking at this plot and you're like, there's only 300 control stars. What happened to all the other stars? Well, I'll remind you, TESS has an inherent 13 days rotation period limit, which means that I can't look at anything above that because I don't know its period. And for this study, we really wanted to know what the period was. And so we went from 57,000 M dwarfs in TESS to just 314 with a less than 13-day rotation period threshold. So what this is saying is either two things. Either the selection effect is real, because in this plot, what we're seeing is the opposite of what was found for the cool stars. In this plot, we're seeing that the control stars have a higher amplitude than the TOIs, which T just stands for test, but they're also still transiting planets. And what this would mean is that if this were a true result, this would mean that the obliquities are misaligned. But we don't think it's a real result. We think it's just selection effects. Because again, we went from 57,000 M dwarfs to 314. And we saw this selection effect in Kepler as well from the main paper. And there was also another paper this year that looked at tests and did a similar, not a similar study to us, a similar study to Mazet et al., where they found that there was a detection, there was a selection effect in tests as well. So in that paper, basically they said, if you wanted to find more TRAPPIST-1 systems, it would be hard because TRAPPIST-1 is an active system. And so as a summary, sorry if I went very fast. We have 3 different results from 3 different projects. The first one is you looked at amplitude versus activity. In this case, the Balmer lines. So H alpha, beta, delta, gamma. In that, we found that that relationship is scattered, which is probably intrinsic. It had nothing to do with magnetic field cycles. So whether or not you take it at the same time or not, you'll see a scatteredly positive relationship. We zoomed in closer to that and we found short-term variability that were flare related, but some of it wasn't. We found 2 kinds of flares. We found non-white light flares, which are weaker, and we found white flares, which were stronger in the corona magnetic fields. And then lastly, we looked at a separate paper from Mazet et al., which looked at amplitude versus effective temperature. And they noticed the relationship that is seen from other stellar obliquity studies, which is that cool stars tend to have aligned architecture with their planets, whereas the hot stars over the craft break were misaligned. So they have a larger range. When checking for selection effects in that paper, they found a similar result, but they didn't check stars less than 6,000 K. And from newer data and from tests, we actually see that that's very important because those have active stars, and we're seeing selection effects there as well. And so the main point of this part was we're missing planets around active stars. And that was it. I probably went fast because it took only 33 minutes.
Okay, now questions. For those of you online, could you raise your hand? And I see Everett.
Yeah, thanks for this presentation. So I was wondering about the flares you showed with the hydrogen lines. It looked like the delta line was a lot stronger than alpha line, and
Yeah.
yeah, that triangle really sticks out. I was wondering if that's understood and
Yes.
what's going on there.
That's accurate. I just didn't mention it. Yes, this was actually, I mentioned this more in the paper, but essentially higher order lines. So when you get bluer, they actually have more variability than H alpha. H alpha is already like what I like to explain is once H alpha reaches saturation, it doesn't get any stronger than that. It just stays there. And it sort of trickles down to like the other Balmer lines. And so you get much more variability there.
I see. Thank you.
And this was also found in a different paper from Durruti et al. They found that calcium HK, which is even bluer than delta, H delta, is more variable than H alpha. But it's a true result. Thank you. Yeah, good question.
Question from audience? Any other question from online? Well, I have a question on to why Everett, do you have another question or is it
I have
your...
another one, but
Yeah.
why don't you go first, and I'll go.
No,
one.
I was just going to ask about the calcium HK because that was my question, and you mentioned that somebody did that study. So when you look at the Balmer line variability and a calcium HNK, because calcium HNK varied more, is it the amplitude was larger or what varied more?
Yeah, sorry. They were looking at equivalent widths. So the strength of the line itself. And I think they converted them to luminosity as well. So in that paper, they were looking at the luminosity and comparing multiple chromospheric lines. And they found that even though several papers in the past have said there's variability in H alpha, there is, but there's more variability in the calcium H and K. And those two tend to be compared directly because H alpha has a lot of different ways it can arise. Many different physics can create an H alpha emission. But calcium H and K is mostly collisional excitation. And so by looking at calcium H and K, you can have like you can have a better understanding of the physics going on. Unfortunately, I can't get that down in that. I can't look at it directly, but I can assume from that paper that if we had gone down to calcium H and K, we would have seen way more variability.
Yeah. All right, thank you. Everett.
Yeah, I was wondering if you could go back to the Mazeh result as a function of temperature, and I'm just wondering, not being as familiar with this, if if you go to so on the left-hand side, yeah, it looks like around the M dwarfs and K dwarfs, it seems like um, there'd be a very strong selection effect to have to planets around quiet stars. So yeah, I'm just wondering. Okay, so it seems like they must be seeing a really strong effect in order to have the KYs here being above the white line. It seems to me like there must be very strong effects since most of the planet follow-up studies would concentrate on the quiet stars. So am I understanding that right? And then why doesn't that happen with the TESS?
So I sort of breezed over this, but essentially this is recreating that study with more Kepler data. And if you look at the one on the right, it's basically showing what they're seeing is mostly controlled by the inactive stars. And for the active stars, we can't really say much because there's not that many planets around there. And so I guess their study is still accurate, right? Like you're still seeing this, except we don't really see much active stars. So there isn't a selection effect, if that makes sense. Like the result is real for inactive stars or stars that rotate faster, more than 13 days or slower. But we don't really know what that is for the active ones because when you have an active star, you have a higher amplitude. And so that's the selection effect that the referee brought up, and it's true. And so that's what we think we're seeing for TESS, that these are very active. But there's also not enough like planets in order to say that this is a real result. And there's also not enough like stars as well. I ran a similar test that the Mazeh et al. Papers did. They did a KS test where they were saying, is this difference real? The answer is yes. For us, no, because we need at least 50 planets in order to say for sure that this is a real result. So we're leaning into it's a selection effect because that's what this other paper found this year as well. And we have several data that shows that. Does that make sense?
Okay, so it's just starting to understand better. So you're saying for a very long period, slow rotator,
Yeah.
the activity there is not going to be as bad, so it won't mean that the planets are preferentially found about quiet stars. Is that right?
No. So
Oh, okay.
yeah, so the yes, the answer is yes to what you said. The bigger issue is because it's active, this means that it has large amplitudes. It means that there's a lot more flares. And so if you would have a small planet transiting it, it might get maxed out. Like you might not see it. That's sort of the idea. And so we don't think that there's less planets around active stars. We just think we're not finding it. We're not finding it. And that's why it's like the sample of test stars we had with planets was 300, but we only found periods around 28 because we have this 13-day limit. So it's not that they don't exist, is that we think we're not finding it because an active star is very complicated, and so we might be missing it.
I see. Thank you.
Okay, any other questions? Right, otherwise we'll thank the speaker again today. And we'll see you next week.
Thank you for having me, and happy Harvest Moon Festival.
Yeah, thank you.
All right, bye.